So in the last two videos, we've seen some different examples of how we can actually integrate different rates to calculate total changes in quantities. But now we're going to take a look at a very specific set of quantities that we're going to be interested in and make sure that we can understand kind of how to distinguish the two. There's going to be an important difference between finding a total distance that is traveled by an object as opposed to computing an object's total displacement. Now, if I think about what these two things mean here, displacement represents a net change. And so quantities of distances are measured as positive or negative. Whereas with total distance, all quantities are regarded as positive. Okay, maybe this makes no sense. If you've spent some time maybe in a physics class, you've dealt with these concepts in more detail already. But I always like the following sort of analogy to just help me process these two different ideas. Think for a moment about a time that you've gone ahead and you've driven in a car. If you've driven in a car and you look at the odometer, right, that's tracking the number of miles that you're driving, then you'll recognize that that value only ever actually continues to tick up, right? You're only adding mileage. So if I was imagining here that I was going to make a trip from point A to point B, if I was going to make the trip in this direction, maybe say I went 5 miles over this way, and then after a little while at spot B, maybe I make the return trip home. Well, if I was to do this, I could see that the odometer would then measure 10 additional miles, right? And so when I talk about total distance that's traveled, I would say, well, I traveled 10 total miles today. That's how far the car actually moved. But displacement is again going to be interested in how far is your start location from your stop location. How much total distance have you kind of ended up different from where you started? So in this scenario, while I've moved a total of 10 miles, when I compare where I started to where I've stopped, I can see that I actually have no change overall. Because displacement is going to think about this 5 miles moving away as maybe like a positive 5 miles, whereas the mileage coming back, it's going to be thought of as like negative 5 miles, and so we can see we end up with 0 miles difference from where we started. So when I think about total distance, I'm thinking like an odometer. If I'm thinking about displacement, I have to think about, wait a minute, I have to think about if I'm, where is my end position relative to my start position? So let's go ahead and take a look here at example number 3 to try to get a sense of kind of how this comes into play with this particular example. Suppose that a particle is moving along a line. Okay, so kind of like what we have here. Maybe it's ping-ponging back and forth between a point A and a point B. Okay. Its velocity at any given time, so the rate of change of its position at any time, is given by this equation. And we'll say that it's measured in meters per second. Well, I'm going to be interested in finding the displacement of the particle during the time period from 1 second to 4 seconds. Well, now the interesting thing here is I have to figure out if there is a difference between total distance and displacement. And here I can clearly see that I'm being asked to find displacement. How do I know how to compute this? Well, one important thing to note here is that recall that whenever I was doing an integral, whenever I was working with an integral, if I was going to go from something like 1 over to 4, then I should recognize that our integral itself, remember, accounted for area that was below the x-axis as being negative area, and area that was above the x-axis was going to be regarded as positive. And so because of this, our standard integral is actually going to compute for us all the time displacement, which is really nice. It makes part A here really, really simple. So I can just say that to find the displacement, I'm just going to integrate my change in position equation. I'm going to integrate that velocity, and I'm just going to integrate apparently from 1 to 4. This is it. This will take into account all the area that's positive and all the area that's negative, and it'll cancel those out, just like our positive 5 and our negative 5 up here were kind of canceling out. So this will indeed measure displacement. Well, again, I have a nice continuous function here, so I can use fundamental theorem of calculus part 2. So if I was to go ahead and integrate, I'm going to get t to the third over 3. minus a t squared over 2 minus a 6t, and I just have to evaluate from 1 to 4. So this is a little bit clunky to work through. There's some kind of ugly numbers here, but it's not too terrible. 4 to the third power is going to be 64. 4 squared is 16. 16 over 2 is 8. And then here I get minus 24. Then I subtract everything when I plug in a 1, so it's minus a third, or 1/3 minus a half, and then minus 6. So of course, if I distribute my negative and simplify everything down, I can get to a final answer. Now I'll leave it to you to double check some of my work here, but I ended up with a total value of negative 9 over 2, which of course would be the same thing as negative 4.5 meters. So what we've measured here is that the object started at a particular location, again, on a line. So maybe the object's start position was here at S, and it moved around, and when it ended its motion after the first 4 seconds, it stopped over here. So this is its finish position. And the total distance from start to finish was 4.5 meters. Since it was below where it started on the number line, we consider that negative. It moved back 4.5 meters from where it started, as opposed to moving over to the right. So this is really all we've learned. But what you'll notice then that we haven't learned is how far the particle actually moved, right? Like if the particle has an odometer, we don't know how far the object actually traversed during that time. Did it move 10 meters? Did it move 1,000 meters? Did it move like 50 billion kilometers? I mean, it's possible, right? It could have been zipping up back and forth along this line for who knows how many times in that simple 3-second period. So if I wanted to find exactly how far the object traveled, there's my total distance. And so I'm going to have to think about each item as not being negative or positive, but rather I'm going to want all the items to be regarded as positive. In my picture, that means I'm going to have to identify where I'm going to have negative and positive areas and think about treating kind of all of them as positive. I want to grab all of the red space like it's positive space so I can understand the total distance traveled. And this is what we're going to calculate here in part B. Now to make this a little bit easier, we can go ahead and note that since we have a function that looks like this, we could go ahead and easily go ahead and try to graph at least a portion of this function. Because we can see that we could graph this, or well, factor this first, and notice that we have a couple zeros on this function. We have a 0 at positive 3 and a 0 at negative 2. So if I was going to go ahead and sketch out my picture here, I can see that at negative 2 and at positive 3, I'm going to cross over my x-axis. And of course, this is a parabola that's going to be opening upwards. So I can see then that I'm probably going to have some picture over here that ends up going something like this. And this is what I'm going to be working with. Let me go ahead and just try to redraw this out a little bit just to stretch it over a bit further so I can imagine where 4 would be. So I'm going to have some sort of a graph that goes, I don't know, something like this, graph not drawn to scale. Okay? But if this is what I have, and I'm interested in measuring the area from 1 over to 4, I should notice that at the start, I'm going to end up with a lot of area here that's going to be underneath my horizontal axis. And so this here is going to be regarded, again, as negative area. But I'm going to notice that anything from 3 over to 4 is actually going to correspond to some positive area. Now, these positive areas, of course, are going to represent positive distance traveled, and this negative area is going to represent negative distance traveled. Just like up here, I thought of moving from A to B as positive and moving from B back to A as negative. But if I want to calculate total distance, I have to kind of ignore the signs. And so I can tackle that in the following way. So I'll say we need to treat all regions as positive areas. But the issue here is that that means I can't just integrate, because when I just integrate, regularly, that's going to treat areas as sometimes negative and sometimes positive. So when I'm calculating distance traveled, I have to go ahead and make a slight adjustment. What I have to kind of do is imagine taking this area here that's negative and making it positive. So that would mean I'm going to kind of be interested in, you can almost imagine kind of duplicating this area, but just up here. So that way I kind of have the same area that's just going to be made positive. And now I can calculate all of this space, which would be a positive amount, plus all that space. So it's the same area just kind of flipped or reflected across that axis. Now what this is actually the same as is that saying that our total distance traveled is going to be equal to the absolute value of our original function v of t. Because remember that the absolute value would take any portion of the graph from 1 to 4 and flip it so that it's positive, right? It would take something that's down at y value negative 2 and bring it up to y value of positive 2. So we are doing an absolute value here. But if you recall back to all of our derivative rules, we have no derivative rules that help us tackle absolute values. And so we're not going to leave it in this form. Instead, what we're going to do is separate things out into areas of our red and our blue space. So I'm going to set up an integral here that goes from 1 to 3. And then I'm going to set up an integral here that goes from 3 to 4. So I know that the second integral here represents the blue space, and so that's totally good. That's going to be positive. But this second integral here represents the red space, and I need to find a way to flip it like the absolute value would flip it. But if I know that this amount is negative, the easiest way to change it from a negative amount to a positive amount would just be to multiply it by a negative. Right? If I multiply this entire amount by a negative, then I would take its negative value and change it to positive. So what I really just have to compute here is an integral. You could imagine I write this as an integral from 3 to 1, right? I could take that negative out using my properties of integrals. I could flip this around. And then I just have t squared minus t minus 6. And then I have my integral here from 3 to 4 of the same exact amount. Now, if you don't like flipping around those bounds, if that's weird, of course you could always just distribute the negative into the actual quantity that we have here and tackle the integral as we would normally. So I'm going to actually leave it up to you to go ahead and actually try to finish out the calculation of this integral. It's a little bit cumbersome to go through and do because there's a lot of numbers here to kind of crunch and throw around, but go ahead and actually give this a shot. So go ahead, try to pause the video here, see if you can compute this all the way out, and then when you unpause, I'll at least reveal the final solution. All right, so hopefully you did actually go ahead and try this out. I know it was a little bit nasty to kind of work through, but ultimately at the end you should have ended up with a value of 61 over 6 meters, and that's about as simple as we can make it here. So if you didn't get this value, you can go ahead and double check your calculations. Maybe you just actually computed something just a tiny bit wrong, but hopefully this is what you were able to come up with. What you'll notice here is that ultimately this is going to be the same, well, I don't have to write squiggly equals, but this is actually going to be the same thing as 10 and 1/6 meters. So this is how far the object actually traveled during that particular time period, a little bit over 10 meters. So while we know that it ended only 4.5 meters to the left of where it started, it moved a total of a little over 10 meters throughout the entire trip. So that's really it for this last section. If you need, of course, to practice these ideas, by all means, please go ahead, take a look at the worksheets or the worksheet that we have associated with this section. And if you come across any other specific questions, by all means, let me know.